Everyone, this is your host Amir Jafari. This is the second lecture on a series of lectures on quantum field theory. Last time, in the first lecture, we answered this question that what is quantum field theory? What's it good for? In which areas of physics it can be used? Questions like this, and the main idea behind quantum field theory. We said that it's the combination of special relativity and quantum mechanics. And special relativity, E equals mc squared, equivalence of between mass and energy, dictates that the number of particles cannot be fixed. So writing down equations like the Schrödinger equation for the wave function of a fixed number of particles is not the right approach if you try to combine special relativity with quantum mechanics. Because the number of particles can change, you need a new formalism which enables you to create and annihilate particles at any point in space and time. And also, you need this mathematical object, the new mathematical object, which allows you to operate on quantum states. For example, operate on one particle state to give you two particle state by creating a particle, or to operate on a two-particle state by annihilating a particle, give you a one-particle state, so on and so forth. So you need this concept of a field and also an operator. So if you combine these two, what you get as a mathematical tool is called a quantum field. Using a quantum field, you can create a particle or annihilate a particle at any point in space and time. And mathematically, it is basically an operator which acts on quantum states by creating and annihilating particles. Okay, so today we're going to repeat the same concepts, basically. But adding more mathematics, we're going to write a couple of equations, simple equations. I'm going to use my pen, finally. And refine that picture. We're going to refine the picture presented in the first lecture to get some, a kind of technical feeling about quantum field theory, at least main ideas behind it. Okay, so let me share my screen here. Well, it's already shared here, but it's small. I can make it bigger. All right, so let's begin with Newton. Okay, Newton was interested in the motion of particles. We are interested in the motion of particles, but we are talking about subatomic particles, very small particles. Newton had no idea about these objects. He talked about large-scale objects like planets. Even in modern language, he didn't know about galaxies, but you can apply Newtonian mechanics to galaxies, the stars. The whole, the solar system. And you can apply it to a dust particle. So the range of scales that Newtonian mechanics can be applied is really large. But still, it fails when you apply it to very small scales of order like the hydrogen atom and smaller than that, and also at high speeds. Okay, so let's write a couple of equations to make what we said in the last lecture kind of more technical and more, kind of precise. Okay, so Newton said, I have this definition. Okay, let me see why I can't write. Okay, F equals ma for a particle of mass m. Okay, if you know the total force acting on your particle mass m, F here, then you can get the acceleration a, which is the second derivative of position with respect to time using this equation. This is the equation of motion. So Newtonian program is as follows. He says, well, give me the position of your particle at any initial time. Okay, call it 0, time 0. Okay, so we're assuming that x0 is given. And also the velocity of that moment of time, initial velocity, so it's v0. If I know these, mathematicians will call these initial conditions, okay? Initial conditions for this differential equation. This is a differential equation. F equals ma, once you know the form of F, becomes a differential equation. For example, for a planet with mass m, orbiting around the sun with mass capital M. X would be in some coordinate system appropriately chosen. You can call this X, the instant position of the planet. And then you solve this differential equation, this initial value problem, and you get the position. Let me write it this way. The position of the particle and its velocity at any later time. Okay, so this is kind of predicting the future. In fact, I'm digressing here, but Laplace, the French mathematician and physicist, after Newton, many years after Newton, was interested in this problem, and he did some work on this. He said, look, you can apply this formalism, what I said, FULMA, basically, Newtonian mechanics, to any particle in the universe. So if you assume that there is an entity, like the God, for example, he called it the demon, who knows the initial value, the initial position, and initial velocities of all particles in the universe, then in principle, it's possible to predict the future. Because the future of the universe, what is it? It's the position and velocity of all these particles. Once you know the position and velocity of all particles in the universe, you know that their acceleration, the forces acting on them, the larger bodies made up of these, smaller particles. So this is kind of a predicting future. If you know all initial conditions, initial positions and initial velocities of all particles in the future, in the universe, sorry. So this is called Laplace demon, okay? But it turns out that this is tricky. There is this problem called chaos. Probably we'll talk about this. In chaos, well, I'm not going to give you a definition here, but chaos means chaos, right? It's a complicated system with some random noises and stuff like that. But here I can give you a kind of clear picture. So let me do this very quickly here. What chaos means is that as a physicist, you know that when you say that I know the position and velocity of the particle at an initial time, you know that any measurement would come with some errors. So when you measure the position of the particle, you're making some errors. Delta x 0. Let's call it delta x 0 for the position and delta v 0 for the velocity. You have some errors. You cannot eliminate them. You can make them as small as you can or you want, but you cannot eliminate them. You cannot take them as 0. Okay. So this means that you're going to get some final errors in the velocity and position of the particles. So you have some initial error, okay, and these are your final errors. In many applications of Newtonian mechanics, if you say that, well, this is small in some sense, I'm not going to talk about that. I'm not going to make it mathematically precise, but you get the point. If error compared with the main value of x0 or v0 is small, the assumption is that the final error will be small as well. And in many situations it is. So this is the case, and you have no problem. Errors are kind of, an engineering problem, so we don't talk about them in physics. However, there are systems, chaotic systems, in which even if you make this initial error in your measurements are very, very small, you're going to get huge errors in the final solution. So these are chaotic systems, okay? We call this chaos. It's a vast area of research right now in applied mathematics and physics. And there are more, even more interesting problems and more complicated problems. In chaos, if mathematically you make this initial error 0, I mean, you let the initial error, go to 0 in the limit, the final solution, the final error will go to 0 as well. In practice, we know that this is not possible. The initial error in measurement cannot be 0. But still, mathematically, if it goes to 0, the final error should go to 0 as well. But there is this super chaos or spontaneous stochasticity, which is super chaos in the sense that even if the initial error goes to 0 in the limit, the final error will be huge and will be infinite in some senses. So this is called spontaneous stochasticity. So by this digression, the point is that even in classical mechanics, there are problems, open problems. There are interesting questions to ask and to answer. So don't take Newtonian mechanics for granted. It's not simple, okay? But it fails at different regimes, including small scales. So at the small scales, what happens? Let's go to quantum mechanics. When you go to very small scales, subatomic particles, for example, scale of smaller than hydrogen atoms, say, there is no certain limit or point that we can say that, well, smaller than this is quantum world, larger than this is classical world. No, it happens actually continuously, but for hydrogen atom, classical mechanics doesn't work. Right. Here you say that, well, look, Newton used X, P, and energy, for example. Newton didn't talk about energy, by the way, but in classical mechanics we do, so let's use the modern language. These are variables, and you can say that I know the exact position or exact velocity or exact momentum. This is momentum, by the way. I'm going to use momentum because it's more common in classical mechanics, in Lagrangian mechanics, Hamiltonian formalism, whatever, and also in quantum mechanics. But it's the same thing, velocity, momentum, difference is just the mass of the particle. And energy is a scalar, x and p are vectors, but these are, variables. These are vectors or scalars. You can measure them. But it turns out that in the subatomic world, this is kind of tricky. Because in Newtonian mechanics, when you talk about a planet like with mass m, like this one that we discussed here, you say that, okay, I have a particle called planet, which is a small ball, and it is at position x. So this is a well-defined expression. But when you talk about, for example, hydrogen atom, let me change my color here. Hydrogen atom, say that this is my proton here, and this is the electron, and this is my position x. If you try to solve this equation and say, look, here F would be the Coulomb force between the electron and proton, you'll see that this doesn't work. Newtonian mechanics doesn't work in the hydrogen atom. Okay, and we know that hydrogen atom is a quantum system. So what happens is that you say, well, this happens for many reasons. I'm not going to go into details of this. I'm assuming that you're familiar with this from your undergrad studies, courses on quantum mechanics. But the point is that at these small scales, particles like electrons are not like little balls. They are something like a cloud, scattered, distributed in space. So they don't have a well-defined velocity, for example. If you look at a cloud, a piece of cloud, a separate piece of cloud in the sky, you can say that, well, I can see it moving, it has some velocity, but if you go closer and closer, for example, when you are traveling on a plane, look at, clouds, take a closer look, you're going to see that it's not well defined. Every part of cloud moves in, different direction. You can't define a velocity vector for the whole cloud. I'm not saying that electrons are like clouds, because it's a classical system, electrons and is a quantum system. But the point is that x, position, p, momentum, energy, e, these are, in the way that we use in Newtonian mechanics, these are large scale concepts. At the small scales, we have to be careful. They become subtle, okay? For example, as I said, the electron behaves like a wave, like a cloud, whatever you can call it, because we don't actually have the right term right terminology for the quantum world because we are large-scale organisms and we are, use large-scale objects. But we call them sometimes wave particles, sometimes waves. But you know that electrons are represented as waves in quantum mechanics. So you say, look, Mr. Newton, we are sorry, but these concepts, in the way that you used, are not applicable to the subatomic worlds. So instead, we are promoting these variables to promotion. I dropped an I here. To operators. Okay. These are operators now. Operators in quantum mechanics. Okay. And say that, well, why we do this? Because if electron is like a wave, I'm not driving quantum mechanics. I'm not talking about postulates of quantum mechanics. I'm reminding you very quickly what we, have in quantum mechanics in practice when we try to solve a problem or think about something like an electron. Okay. You say that an electron or any subatomic particle behaves like a wave, and what we know about this wave, what we can know about this wave, Dubroy wave, is a wave function, which is a function of space and time. Let's call it psi. Okay, and this wave function is a complex function, and its complex module, which is defined this way, psi star is the complex conjugate of psi as a complex function. This gives you the probability density of finding the electron or the particle in a given volume in space. For example, if you integrate this over some volume in space, okay, this is the probability of finding that particle that you're working with in that volume in space, okay? And if you integrate from infinity to infinity, if you look at everywhere in space, you should get unity because the particle is somewhere, okay? You should be able to find it if you look everywhere. Okay, so then you say that a wave in classical physics is something like this. Ipx minus et, right? H bar. Now I have H bar here, and again, assuming that you are familiar with this constant, with these constants, with this, with these equations, basically, because you've taken course on quantum mechanics. Otherwise, you wouldn't be watching this video. Okay, so if you take derivative of this function with respect to x, you're gonna get what? I p h psi. What happened? I don't want it. Okay, psi. And if you take the time derivative, you're gonna get minus I e over h psi. Okay, these are just simple derivatives with respect to time and x, and you have a simple exponential function. Okay, this means that this p, momentum, is basically a differential operator. Okay, minus I h d over dx. When you act this differential operator on psi, the wave function, it gives you this. So you can define the momentum operator by this differential operator. And also for E as an operator, you can get this differential operator. So you see that, and x remains x in position, representation. We're not going to go into details. So this is what you get for this function, for this wave. So because we are representing particles as waves, so we get this picture that momentum and energy and position itself are differential operators or matrices in the Heisenberg picture, but we're not going to talk about that. Okay, so this means that you're promoting these variables These are variables in Newtonian mechanics, in classical mechanics, but you are promoting them to operators. This is called the first quantization. Try to remember this if you don't know this, because we're going to have second quantization, which is a misnomer, but unfortunately it is used. So if you remember the first quantization, which means that x, p, e, variables like this, which are variables in classical physics, are promoted to operators, for example, differential operators, and we call it first quantization. It will, make your life easier in order to understand what second quantization is. Okay, so this is basically, wave mechanics. Okay, Schrödinger's, mechanics. Then you say that, well, okay, now the energy of a particle, what is it? In classical mechanics, we call it Hamiltonian, right? Let me change my color again. So here, okay, you say Hamiltonian H. Now it's like energy, right? It should be an operator again because it's the kinetic energy of the particle, which is a function of momentum. Momentum is an operator. So the whole energy of the particle, the Hamiltonian, should be an operator, a differential operator in this, wave mechanics picture. Times psi, you have now differential operator acting on psi. Here you have an exponential function, but it can be more complicated function. So you should get this. I mean, this is a kind of a trivial, energy relation, if you like. Okay, Hamiltonian is the same as energy, but Hamiltonian is in classical, in non-relativistic mechanics, is given by p squared over 2m. M is the particle's mass, and p is the momentum, plus some potential energy, which should be treated as an operator now, psi, and E is IH d psi dt. So this is the Schrödinger equation, because P is a differential operator. You can write it like minus IH d dx squared over 2m plus V psi IH d psi dt. And from here, this is one-dimensional. This is the one-dimensional case. In 3 dimensions, instead of this, you're going to get minus IH, the gradient operator, derivative in 3-dimensional space. So finally you get, oh, sorry, there is no I here, because I'm squaring P. So you get this general equation in 3D. IH d psi dt, which is the Schrödinger equation. You are familiar with this. Okay. Again, I'm not driving the Schrödinger equation. I'm reminding you of what we have here. So you solve this equation for psi, for any system, for example, the hydrogen atom, and you get the wave function. And the wave function psi gives you the probability of finding the particle at any given volume v in space. And using this formalism, you can get the energy eigenvalues, the allowed energy levels of the system. For example, Schrödinger himself in 1924, applied this equation to the hydrogen atom and got the energy levels, energy, eigenvalues, etc. And this was the first, successful application of this theory to the hydrogen atom, and then later was applied to, heavier atoms. Okay, so this is the Schrödinger equation. Now, we are not interested in any details here about, how you apply it to an atom or how you apply it to heavier atoms, etc., assuming that you are familiar with the general formalism, how we do this. What I'm interested here and what is needed here is the fact that this is a non-relativistic equation. Okay, it's quantum mechanics, but it doesn't, it doesn't basically obey special relativity, because here I use this expression for the total energy of the particle, the kinetic energy p squared over 2m plus V, the potential. I'm gonna ignore this potential because it's not really important here. But this expression for the kinetic energy of the particle is the classical expression. Okay, so in order to combine special relativity with quantum mechanics, one might say that, well, now instead of this classical expression for the kinetic energy or the energy of the particle, let's use this Hamiltonian, p squared c squared m squared c4. C is the speed of light, p momentum, m particle's mass. This is the relativistic, relation for energy, basically. Okay, and then say, okay, this is the relativistic expression. I can make it an operator by writing P as an operator. Again, P is given by minus IH radiant. It's the momentum operator. So I have an operator for the Hamiltonian. But the problem is that if you use this Hamiltonian, you have to deal with this difficulty. Let me write it. If you write this energy relation, you're going to get something like this, minus h squared c squared 2m Laplacian plus m squared c4 times psi ih t psi dt. Okay, and you can see immediately that there are a couple of problems here. One problem is that, well, there is Laplacian here inside the square root. How can you make sense of that mathematically? Well, you can use Fourier transform, or you can Taylor expand the square root function. But again, you're going to have difficulties there. You're going to have, for example, infinite terms, infinite number of terms. But there is a more serious problem, and that is, well, in special relativity, we know that space and time should be treated on the same footing. So here you have first-order derivative with respect to time, but second-order derivative with respect to space, x. So space and time are not treated on the same footing. So this formalism, this approach doesn't work for this reason, okay? And other reasons, but this is the more serious one. Well, you would say that, well, okay, I can fix it. I can write this equation again, okay? But I'm gonna write it this way. By squaring these differential operators, both sides of the equation, I can use the relativistic expression, but now I don't have the square root function, so I don't have that problem, right? You get this. And you are kind of right. This is the Klein-Gordon equation. Klein-Gordon, it has a very interesting history. Schrödinger himself got it in 1924, before he got his non-relativistic equation, which today we know as the Schrödinger equation. But he dropped it, he discarded it, because it gives you some nonsense about probabilities. Remember, here in the Schrödinger equation, the non-relativistic case, we interpret psi, the wave function, as a probability amplitude, okay? And it gives you the probability of finding the particle at any given volume in space. But here you can't have that interpretation, because the probability density, if you define it for this equation, can be negative. Remember, here I should emphasize that P is a positive definite function. Mathematically, by saying that it's a positive definite function, we mean that it's a function whose value is always positive or zero. It cannot be negative, okay? So it's a positive definite function. But here it doesn't happen. If you define a probability density, it can be negative, so you lose this, interpretation of the wave function psi as a probability amplitude. You lose this probabilistic interpretation. So Klein-Gordon equation has this problem. Again, you can kind of try to fix this problem by saying that, okay, I'm not going to interpret psi as the probability amplitude. I'm going to multiply it by the charge of electron, the fundamental charge, and I'm going to interpret this as the electric charge density in space. You can do this. This is done in textbooks on relativistic quantum mechanics, but still it doesn't work. I mean, we're going to see the main reason why it doesn't work, and I've already told you why. Because in this equation, when you write, let me repeat it for you. Because in this equation, I've written m. What is m? The mass of the particle. What particle? The particle you are working with. So you're assuming that you have one single particle you are working with, and the number of particles in this theory is fixed. You can write down this equation for multiple particles, for n particles. Also, the Schrödinger equation. The Schrödinger equation for multiple particles, for n particles, can be written easily. But the point is that because you have this mass here, the masses of particles, if you have many of them, the number of particles and type of particles, their masses are fixed. You cannot change it. But we know that because E equals mc squared, we talked about this before many times, it dictates that the number of particles cannot be fixed. It's going to change because if you have energetic particles, that energy can give you new particles, okay? So during an experiment in particle physics, you're going to see new particles popping out, as I said before, and you need a new formalism to deal with this situation. But it took some time for people in 1920s and 30s to come to this conclusion. For example, Dirac, after Klein-Gordon and Schrödinger, and many other people actually obtained this Klein-Gordon equation, this relativistic equation, and discarded it or worked on that. Then Dirac, I guess in 1928 or 7, okay, something like that. He said, look, this problem of probabilities being negative, probabilities being negative. So sometimes can be positive for the Klein-Gordon equation, sometimes negative, but this is the main problem. Mathematically, Dirac was an excellent mathematician as well, but this is not hard to see that this problem, probabilities being negative for the Klein-Gordon equation, this problem arises because you have second-order derivative here, second-order derivative with respect to time. Okay, this is the source of problem. So Dirac said, look, I'm going to use again this energy relation, okay, and I'm going to leave the right-hand side of the equation as it is, but I'm going to write a Hamiltonian which is linear in momentum, okay. It's not second order in momentum. So he was trying to avoid this second order derivative here and second order derivative here. Keep everything linear, okay, in time and space. And he got his famous equation. We're not going to need, its detailed form, but let me write it for you. In some notation, there are different notations for Dirac equation. We're going to study Dirac equations at some detail in the future. But you can write it in this form, I guess, if I remember it correctly, right? Something like this. These gammas are matrices. You have 4 of them, gamma 0, 1, 2, 0, 4 by 4 matrices. And this d mu is the relativistic derivative. Derivative with respect to time and also derivative with respect to space together as a 4 vector. Okay, so this is the Dirac equation, but still, you have the same problem. You have this m here. What is it? The mass of the particles that you are working with, and the number of particles is fixed. But the Dirac equation does not have that problem with probabilities. Okay, probabilities are positive definite here. But there is another problem. The other problem is that the problem with the Dirac equation is that it leads to negative energy states, negative values for the energy of the particle. Dirac was clever enough to find a solution, kind of solution for that. He said that, well, an electron can absorb a photon and go to a lower state, lower energy state, and what it leaves behind acts like a hole with a positive charge because electron has left it. The hole acts like a positive charge, so this is Dirac's hole theory. But still, the problem is that that electron can go to lower and lower and lower energies. There is no limit for the energy. There's no any lower limit for the energy. So electron can lose energy and go to lower energy values. So the whole theory is kind of, maybe promising, but remember, the Dirac equation is written for a particle with mass m. So you are working with a picture in which you have a single particle. But then you have this whole theory, many particles, infinite number of particles. So it's kind of confusing how many particles you have. So for reasons like this, the Dirac equation doesn't work as well as a relativistic, extension of the Schrödinger equation. So it looks like that we are kind of, stuck here. And the question is why we are following special relativity in writing these equations, in trying to generalize the Schrödinger equation to the relativistic case, but we fail for different reasons. Why is that? Why we cannot combine special relativity with quantum mechanics? You already know the answer. It's here. E equals mc squared. Well, you are writing differential equations for a fixed number of particles. For God's sake, it doesn't work, obviously, because E equals mc squared. Energy and mass are equivalent. And when you start with one particle, for example, in this case, say Dirac equation for a one particle, because that particle is relativistic, you are trying to combine special relativity with quantum mechanics, right? So you are working with high energy. High energy means that you can convert that energy at some time into new masses, new particles. So new particles can be created. So this approach doesn't work. I told you before about this, writing down wave equations like the Schrödinger equation for wave functions for a fixed number of particles doesn't work because E equals mc squared. But I wanted to write down a couple of equations, familiar equations perhaps for you, to see what's going on in practice. Okay. So we're going to abandon this approach. We're not going to try to write down differential equations. We need a new formalism, again, as I said before, which enables us, one, again, let me change a new formalism is needed, which enables us to create and destroy particles at any point in space and time, x and t. Okay. And also, we need, again, a formalism with a tool, a mathematical tool, which operates acting on quantum states. So if you combine these two, what we need is a new mathematical tool, not differential equations, not wave functions, no, a new mathematical tool which can be called a field operator. Okay, we need field operators and we call them quantum fields. Okay, so what does it do for us? Well, it can operate as follows. Like let's make it simple. You are in the state of your system has no particles. Okay, you have no particles. You have vacuum. The vacuum is the state, the quantum state in which there is no particle. Let's use Dirac's bracket notation and call it 0. This is the vacuum, okay, vacuum. Then you need something like this. I need an operator which creates, let's call it A plus, okay, creation operator, which acts on this vacuum and it gives me a one particle state, the quantum state in which there is one particle living, for example, an electron. So this operator, this creation operator, acted on the vacuum and gave me one particle, okay, gave me one particle state. It can act again on one particle state and can give me two particle states. Now, where this happens? Well, in space. Where in space? Anywhere. So it's a function of x and t. X and t. Okay. So you see it's a field because it acts on at any point in space and time. And also it's an operator. So let's put hats on it because it acts on quantum states. Okay. It also should have another part, if you like. Let's call it, so this can go forever. Okay. 3 particle states, 4 particle states can be created the same way. The annihilation part of the field or annihilation operator acts on one particle state and gives you your vacuum back, okay, by annihilating the particle in that state. It can act on 2 particle state, give you 1 particle state, so on, so forth. So again, where in space and time? So it's a field, or we can interpret it as a field. So we say that, well, I need this field, okay, which has 2 parts, creation part and annihilation part, xt. Okay. The reason that I use this symbol here is that, well, it's not an equality. We have some Fourier transforms, stuff like that on the right-hand side, and there are different representations. Number representation, for example, for these fields, but we're going to talk about the technical details later. The idea is that you need a field which is at the same time an operator. We call it A, okay? This is a quantum field. So this quantum field is a field because it can give you a particle. It can create a particle at any point in space and time, or it can destroy a particle at any point in space and time. It's a quantum field because it acts on quantum state. You can, think of it this way. So this is the gist of it. This is a quantum field. Okay. Now we can use this terminology that this field A fills space and time. Okay. It's present everywhere. Now, if you want to create a particle, it acts there and gives you a particle. If you want to annihilate a particle, it acts on that at that point that you like, wherever it is, and annihilates a particle. So in some sense, you have something present in space and time. So you can think of quantum fields in this way. Imagine that space and time is a swimming pool. Again, I'm repeating this example. I gave this example before in the first lecture. And the surface of water here, well, I have to use color blue for water. Okay, you have water here, and it's quiet. Okay, no one swimming, there is no wind, nothing there. This is your vacuum. Space-time is a swimming pool. Okay, depth of water here, h, as a function of position and time, acts like a field. At any point in your swimming pool on the surface of water, you have a value for this h, so it's defined everywhere in space and time. As time passes, h can change at any given point. For example, if there is a wave, there is wind, for example, and it causes some waves, it creates some waves, so h can change, in a very complicated way. So the point is that you have a function, depth of water, which can be thought of as the field, a scalar field. It's a classical field. It's not an operator. It's not a quantum field. It's not acting on quantum state. No, but this is an analogy, okay? So now you say that, well, I have vacuum. Okay, so what? Then we say that, well, remember, in quantum mechanics, you represent particles, like the electron, for example, by a wave, using a wave, okay? So if you have a wave like this, let's do it this way. So it's a wave packet, okay? A particle can be represented this way. This is quantum mechanics, ordinary quantum mechanics. So waves are particles. If you have one wave, you have one particle. You are in one particle state. If you have two waves, okay, propagating here, two waves, you are in the two particle state, so on and so forth. This is quantum mechanics. But you cannot change the number of waves. Again, I'm using this as an analogy, okay? This is not a derivation, this is not a mathematically rigorous way of thinking about quantum mechanics, but this is an example, okay? You say that this is quantum mechanics, okay? Waves, particles, I have two waves, I have two particles, so on and so forth. But how to create waves? You say that, well, I can drop a pebble and it can create some excitation here. Let me, okay. An excitation here would be something like this. You drop a pebble and it gives you some waves. So you excite this function h at a given point in space and time, and that excitation, that change in the field, depth of water, can be thought of as a particle because it creates waves, and waves, quantum mechanically, are representing particles, okay? They are particles. So this way you can think of quantum fields filling space and time, like the water. A quantum field is something like the depth of water. It's a field defined everywhere. When you try to create a particle, you excite the field at a given point in space and time, and that excitation, by giving energy at that point, that excitation creates some waves, and those waves are particles, okay, which is familiar from quantum mechanics. So particles are represented as excitations in the field. Particles are excitations in the field. So for example, if you are the quantum field, and this is just an example, this is an analogy. Don't take this very seriously, but you can use it as as a tool to visualize what's going on, at least. For example, if you're working with electrons, you're going to have electron fields. You can call them AE, electron fields. If you are working with quarks, you're going to have AQ, quark field. If you are working with I don't know, any other type of particles, you are working with that field. Any type of particle has its own field. You have, for example, the electron field, filling space and time. When there is no electrons around, you are in the vacuum state of the theory. And when you try to create a particle, the electron, in this case, one electron, you excite this field, and that excitation, by giving energy, spending energy at that point in space and time, that excitation represents a particle, okay? So this is the main idea behind quantum field theory. Excitations are particles. are interpreted as particles. Now the problem here, that's it for lecture 2, the second lecture. We can end here. But the question is, okay, this kind of makes sense perhaps, but how we get these fields, how we get these A plus, A minus creation and annihilation operators? Is there any differential equation for, for any field like the electron field, or what this means? This sign over here, is it an equality? How you write this? How you separate a field, the creation, annihilation, and annihilation part? Okay, so these are questions to be answered in the next lecture. But the main problem here is that, well, you are talking about an excitation here in the surface of water, okay? How we represent an excitation mathematically? How should we approach this problem? How should we formulate this excitation in a way that can be interpreted as the creation of a new particle? Okay, think about this. Take a walk, get a coffee, think about this. Now we know that particles are represented as excitations in a quantum field, but how we, formulate this excitation, how we write equations, what's the formula, in a simpler language, what's the formula for that excitation, how we write equations for that excitation? This is one question you should think about. And also, how we get these operators, as I said, what kind of, do we have differential equations for them or not? How we get these operators mathematically? Solving differential equations, solving PDEs, solving what? Well, how we get them? This is another question, and these questions are related, okay? It's going to turn out that these are related in a very, well, elegant way, okay? You can call it an elegant way. And this is going to be discussed in the next lecture. But I invite you to get a cup of coffee, take a walk, think about this. You're now familiar with the basic concepts behind quantum field theory in a very primitive way, but still, it's the framework we have. So think about this. How we get these creation and annihilation operators, how we get these quantum fields, and also how we formulate this excitation as a way to create particles. The key word is simple harmonic oscillator. Okay. I'm not going to discuss this now, but this is the key word. Probably you're familiar with this. If you are not familiar, get a textbook on quantum mechanics and review the quantum simple harmonic oscillator. How in quantum mechanics we formulate or approach the problem of simple harmonic oscillator. This is going to be useful in the next lecture.